Alright, welcome back guys. Now that we've effectively loaded our image into our notebook, we can get started on implementing style transfer. We have already discussed what style transfer is, but it's equally important to discuss just how it is achieved. In order to achieve style transfer, it must first be possible to separate the style of an image from its contents. After this, it should also be theoretically possible to transfer the style elements of one image to the content elements of the second image. This is done using mainly feature extraction from standard convolutional neural networks. These features are then manipulated to extract either content information or style information. So let's discuss just how this happens based on the style transfer paper mentioned earlier. You can find this paper in the resources folder within this section to get a more in-depth understanding of the process. This process involves three images: a style image, a content image, and finally, a target image. The style of the style image is combined with the content in the content image to create a final target image. Check out this video created by Elliot Andrus that shows the entire process of style transfer and the steps that it involves. If it looks overly complicated to you right now, that is completely alright, as this is just meant to give you a full overview of style transfer. We are going to run through the theory and code behind style transfer, and we will revisit this video again, and hopefully then it will make a lot more sense to you guys. This process begins by selecting a few layers within our model to extract features from. This essentially just means extracting the output of the model prematurely at a few different locations in the model. By selecting a few layers to extract features from, we get a good idea of how our image is being processed throughout the neural network. We extract model features for our style image and our content image as well. We then extract features from our target image and compare it to our style image features and our content image features. In simple terms, you want the content features of the target image, whatever that image may result in being, to match the features of the content image. You want the style features of the target image, again, whatever image that may end up being, to also match the features of the style image. So, moving along with our code, let's define the function that will allow us to get features from our images. This is going to be a simple function with only two arguments. The first one being our image that we want to extract features from, and the second being our model that we are going to use to actually extract these features. So inside this function, the first thing we are going to do is choose the specific layers within our VGG19 model that we are going to extract features from. Let's do so by defining a layers dictionary object. Layers is equal to, and that will contain the specific layers that we are interested in extracting features from, with their respective layer number in the model architecture. And do note that when choosing the layers we want to extract features from, we are simply going to follow the layers provided by the style transfer paper that I mentioned earlier, as the results they obtained were phenomenal. You can feel free to play around with these layers to get your own unique results. The layers chosen by Gattis and al. Were the first layers in each batch of convolutional layers. Revisiting the model architecture, you can see 5 batches of convolutional layers. The following convolutional layers were chosen for feature extraction: conv11, conv21, conv31, conv41, and conv51, where the first number represents the specific batch of convolutional layer, and the second number represents the specific layer within that batch. This figure effectively labels all the layers in this model. Alright, so what we can do is scroll up to the model summary and map these specific layers to their layer number within our model. Conv11 is clearly 0, conv21 would be 5, conv31 would equal 10, conv41, 19, conv42 would be 21, and finally conv51 would be 28. So let's take this image and use it to fill our dictionary object with the appropriate mapping. We will map 0 to conv11. We will map 5 to conv21, 10 to conv31, 19 to conv41, don't forget your comma, 21 to conv42, and finally 28 to conv51. Now we have 6 feature extraction layers. We are going to use 5 of these for style extraction, while using only one of them for content extraction. We are going to use conv42 for content extraction, as only a single layer is sufficient for extracting content. This layer is also deeper into our neural network and will provide high-depth image features. This is due to the fact that pre-trained object detection convolutional neural networks become very effective at representing content elements. The further you follow the image data through the network, the more pronounced these content elements become. This is mentioned in the style transfer paper by Gatiss and al., found in the resources folder of this section. And now matching these content features with the target image features will allow for optimal content creation in the target image. The remaining 5 layers will be used for style extraction. Getting style features from various layers throughout the network, allowing for optimal style creation, as style as opposed to content is more complex to recreate. Extracting style features from numerous layers will allow for the most effective style extraction and recreation, as more features will give a more complete picture of these style elements. And now that we've selected the layers we want to extract features from, let's move forward and actually extract these features. We begin by defining an empty dictionary called features, which will simply store all the extracted features. And now what we're going to do is run through our model and fill up our feature dictionary. So we'll be running a for loop, iterating over all the layers in our model. Dot module dot items object. And now what this will do is return relevant modules from our model. In this case, we are returning all the layers in our model. And the layer variable stores layer information. We are also going to need to access the layer name to implement the dictionary element that we defined earlier. The layer name unexpectedly actually returns the integer number labeling the specific layer. So for example, for the conv11 layer, the name variable will contain the value 0. Now with each iteration of this loop, we are going to run our image through the specific layer, layer image, through the specific layer that we're looping through, storing this inside a new image. Image is equal to layer image. This essentially feeds our image through our network, as when the original image is fed into our first layer, the newly defined image object stores the output of that first layer. The output of the first layer then becomes the input for the next layer, and just like that, the process continues until our image has cycled through the entire model. Now, while this for loop will cycle through the entire model, we want to extract features from the model layers that we defined earlier. So let's add an if statement. If, which checks the name of the current layer we are iterating through, is inside layers. we check and see if it's inside the layers dictionary object. And if this is true, then we are going to store the output from that specific layer. This is done by accessing our features dictionary and defining a key, which we set equal to the current image value. And now what we can do is use our layers dictionary to convert the name of our layer into a proper string name. For example, using the name as 0, our dictionary will convert conv11. We then store this string name as the key associated with each image value in our features dictionary. This will make it simpler to use our features dictionary later, as the keys will simply be layer names. Alright, and now finally we are ready to conclude this cell by returning the features dictionary. Like so, return features. And now running this cell and solidifying our function, we can move on and actually extract features from our content and style images, making a call to our getFeatures function, getFeatures, with our content image and our VGG model as the arguments, and we can store the returned feature dictionary into a variable called content features. And now simply copying and pasting the following line, we can replace the content image with a style image and store it inside of style features. And now that we've effectively gone into our VGG model and extracted all the relevant features that we wanted for our content and style images, the content features are good to be used as they are, as the convolutional network normally will do a great job of extracting content elements from any image that is input. The style features extracted, however, require one additional processing step to be more useful. We look into that in the next video.